I'm Dr. Roger, and today we're looking at differential equations, in particular the Laplace transform of the Dirac delta function. I'm looking at d tau of t minus t0, which is defined to be 1 over 2 tau from t0 minus tau to t0 plus tau and 0 everywhere else. So that's graphed here, and clearly the integral of d tau t minus t0 dt from negative infinity to infinity equals 1 regardless of what value of tau we have. And I'm going to define the Dirac delta function, delta of t minus t0, as the limit as tau goes to 0 d tau t minus t0. For any t not equal to t0, eventually d tau of t will be 0, so this limit will be 0. For t equals t0, this limit is undefined. It's growing toward infinity. So this is not actually a function. The value of delta of t0 is undefined. This is a generalized function or functional. You may learn about this in real analysis or some other course that covers measure theory, but we're not going to worry about that. We're going to pretend it can be treated like a function, and it turns out that this is true. And we're going to say that the Laplace transform of the Dirac delta function of t minus t0 is the transform of the limit, which is the limit of the transforms. So the limit tau goes to 0 of the integral from 0 to infinity d tau t minus t0 dt. Oh, left out my exponential. E to negative st d tau of t minus t0 dt. And writing this piecewise, that is the limit tau goes to 0 of the integral from 0 to t0 minus tau of e to negative st. In that interval, d tau is 0. So that's 0. Plus limit tau goes to 0, integral t0 minus tau, t0 plus tau of e to the negative st, 1 over 2 tau, dt, plus the limit tau goes to 0, integral t0 plus tau to infinity of e to the negative st, and again times 0. And again, this third integral is 0. So I'm only integrating this one expression, and that is the limit tau goes to 0. The integral of e to the negative st is negative 1 over s, so I get negative 1 over 2s tau e to the negative st from t0 minus tau to t0 plus tau. So that's limit tau goes to 0. Negative 1 over 2s tau e to negative s t0 minus s tau, and then minus, at the lower limit, minus a negative is plus 1 over 2s tau e to the negative st0 plus s tau. going to erase this since we've seen where this is coming from. And this equals limit tau goes to 0. My denominator is 2s tau. I'm going to take this first. I'm going to apply an exponent rule and write that as e to the negative st0 e to the s tau, and then minus my second term, which is e to the negative st0 e to the negative s tau. So I can write this as limit tau goes to 0 e to the negative st0 times over s tau times e to the s tau minus e to the negative s tau over 2. This is hyperbolic sine, so I'm going to replace it with hyperbolic sine, and I get limit tau goes to 0 e to the negative st0 hyperbolic sine of s tau over s tau. Well, this is a good time to apply L'Hopital's rule. I'm just checking that everything's on camera, so we're good. And L'Hopital says this is, since hyperbolic sine goes to 0 as the expression you're taking the sine of goes to 0, and your denominator also goes to 0, I can take the derivatives of both, e to negative st0, and this is by L'Hopital. L'Hopital's rule says the derivative of sine, hyperbolic sine, which is hyperbolic cosine, times, from the chain rule I get an s, derivative of s times tau. The tau derivative is just s. S over s is 1, and as tau goes to 0, hyperbolic cosine of 0 is 1, so this is e to the negative s t0. So I can add to my table of Laplace transforms that the Laplace transform of the Dirac delta function at t minus t0 is e to the negative s t0. And it turns out that the Dirac delta function and piecewise functions are two of the primary reasons that we use Laplace transforms. So this is one of our important transforms. Come back soon for my next differential equations video. With math, there's always more.